Swayam Prabha. Digital India. Educated India.
Welcome to this lecture number 15, in which we will continue with the previous lecture, that is the unsteady radial flow in leaky aquifers. And here let us start with the sketch, actually the diagrammatical sketch, in which there is a well, it is fully penetrating into the leaky aquifer, and so this is the water table, and here for simplicity we are considering this aquitard, that is the semi confining layer, only at the top, although actually the aquitard can be at the bottom also instead of the top, or it can be both at the top as well as bottom, which was briefly listed in the previous lecture. But for simplicity we are considering only the top aquitard or the top semi confining layer. So this is, and the bottom confining layer is fully impervious, so this is the aquitard, that is semi confining layer, so it is a top, or rather aquitard at the top, and this is the impervious confining layer at the bottom, and this well is fully penetrating. And here let me so this is the water table, and here there is radially inward flow into this well, which is fully penetrating into the leaky aquifer. So here let me mention here, so this is the well fully penetrating a leaky aquifer. So here this is the this is the unconfined aquifer, and this is the leaky aquifer. And this unconfined aquifer and this aquitard, and through this aquitard, so there is some contribution of groundwater into the leaky aquifer. And here, so this aquitard at the top, so it has, so the hydraulic conductivity that is K dash, and similarly this leaky aquifer, so with the hydraulic conductivity K, and this one, the thickness of the aquitard is B dash, and similarly the thickness of the leaky aquifer is B. So, with this, that means K and B represent the hydraulic conductivity and the thickness of the leaky aquifer, while K dash and B dash represent the hydraulic conductivity and the thickness of the aquitard, which is situated at the top. So, with this definition sketch, so this is the definition sketch, and yesterday, I am sorry, in the previous lecture, so it is the expression for the leaky aquifer well function was written as follows. So, this is denoted by W of U comma R by B, where this B represents an equivalent aquifer thickness. That means it is a thickness which represents the equivalent of a leaky aquifer at the bottom having a top aquitard. And here, so this is the Thais, the modified Thais equation is the leaky aquifer well function is that is W U comma R by B, and here obviously this U is R square into the storage coefficient divided by 4 transmissivity into the time since pumping, and then this R by B. So, this R by B R by B is it is R into under square root K dash, which is the hydraulic conductivity of the top aquitard, divided by K into B dash. So, this can also be written as R divided by under square root T, that is the transmissivity of the leaky aquifer, divided by K dash by B dash, which is the ratio of the hydraulic conductivity of the top aquitard as well as the thickness of the top aquitard. So, this represents, so this bottom the denominator, that is square root of T divided by K dash by B dash, that is equivalent to this B. Here, and with this definition sketch as well as this parameter. So, now the equation for the drawdown is given by this Q divided by 4 pi into the transmissivity of the leaky aquifer multiplied by the leaky aquifer well function, that is W U comma R by B. B is the capital, it is capital B, which represents the equivalent thickness of the leaky aquifer as well as its which is confined by a top equitard or top semi confining layer. And here, so this one, and here let us consider in case of a fully confined aquifer. So, what happens is this in case of fully confined aquifer, so this K dash, that is the hydraulic conductivity of the equitard, becomes 0 because it is fully confined at the top as well as bottom. So, here for a fully confined aquifer, K dash is equal to 0. So, this implies that B tends to infinity and therefore, this W, that is the U comma R by B, becomes WU, that is leaky aquifer well function. So, this becomes, this gets transformed into this confined aquifer well function, which is simply known as well function. So, therefore, so this is so this relationship for the drawdown in terms of the pumping discharge as well as the transmissivity of the leaky aquifer and this U, which is the well function parameter, which is R square into storativity divided by 4 T into T, 4 times transmissivity into the time since pumping, comma R by B, where so this R is the radius of the well as well as B is the equivalent thickness of the leaky aquifer as well as the top equitard. So, this one, and here also we can there is a graphical method similar to the type curve which was followed in the aquifer, in the confined aquifer. So, here also that similar method can be used here also. So, what is done here is, so there is a log plot of log of W U comma R by B versus log of 1 by U, and then another. So, this is the type curve. So, this is the type curve for leaky aquifer. Similarly, there is if we plot the drawdown, that is log of S versus log of T. So, this is the field curve for the leaky aquifer, and both these will have a similar shape of the this one. And here what is done is, so in this case, say this may be here there is in the field curve. So, there will be different points depending upon the, and here this is the leaky aquifer well function, which already we discussed in the previous lecture, and here, so this will be something like this. So, if we match the field curve over the type curve, so that most of these data points on the field curve will overlap or will lie more or less on the almost on the type curve. So, in that case, while at the same time maintaining the parallel nature of the axis. So, this is so here I am just and the next is this one, the field curve, and then so this is the matching, that is matching point determination. So, this is the graphical method for determining leaky aquifer parameters. Formation constants. So, here what is done is, so the firstly there is the type curve having this log of W u comma r by b versus log of 1 by u. So, it will have a this kind of a nature, and then so here, so it is matched with, so this is log of t and this is log of s. So, wherein we have a number of data points like this. So, in this case, so this is the matching point. So, this is the, and once we do that, so for any using any point, we can get the we can determine the leaky aquifer formation constants such as the transmissivity and storativity. So, for any point, so here let us say typical matching point, in this case, so this represents log of s, and similarly this represents log of t. So, this is log s for matching point. Similarly, this represents log t for matching point, and this represents that is log W u comma r by b, and this represents log W. And so, therefore, here what you can do is, using this matching technique, we can determine the formation constants of the leaky aquifer. So, by this matching technique, so that is we know this S versus T. So, in that case the corresponding this one is there. So, therefore, this is u is equal to r square S divided by 4 T T. So, here this based on the matching point 1 by u is known. So, therefore, u is known, log of 1 by u is known. So, therefore, u this 1 by u is known and u is known, and then this time is known, and then this r, which is the radius of the leaky well fully penetrating through this, that is known. So, therefore, we should be able to calculate the this one, the so this is one equation, and then secondly we have the other equation, that is S is equal to q divided by 4 pi t into W of u comma r by b. So, here this is known based on the matching point. So, this is known. So, therefore, T is equal to, that is q divided by 4 pi into S into W u comma r by b. So, this is for the, so this is for the matching point. Once this T is known, so then, so this is here you can call this as equation so this you can call as equation 1. So, therefore, using this equation 1 in the expression for the well function leaky aquifer well function parameter, that is u. So, we can determine the storativity of the well function storativity of the leaky aquifer is equal to u into 4 T T divided by r square. So, this is for the matching point. So, this is also for the matching point, this is also for the matching point. So, this is equation 2. So, like this, once we match the both the curves similar to the one which we did in the confined aquifer, so similar to the one we did in the confined aquifer. So, here we are matching the individual points on this pumping test based on the pumping test data, wherein the drawdown as well as the time since pumping, that is plotted in this curve, which is the field curve known as the field curve, and we match that with this the plot of, that is the it is the Walton's theoretical curve for the leaky aquifer. So, this is the type curve. So, this is also the Walton's theoretical curve. So, using this and matching, so maintaining the parallel nature of the vertical as well as the horizontal axis. So, you get the matching point, and then for any point, so we will get 4 different values of log of the leaky well function parameter, as well as the log of 1 by u, log of leaky well function, as well as log of reciprocal of the leaky well function parameter, and the log of drawdown, as well as the log of the time since pumping. So, then simply substitute all these values and then obtain the transmissivity, and firstly the transmissivity using this expression, that is the modified Theiss equation for the leaky aquifer, as well as from that the storativity of the leaky aquifer using as per this equation 2. So, like this we can solve leaky aquifer, and of course imagine, and here you can imagine how involved it is. So, here we are considering things which are simply we have simplified it to a great extent. So, that means, although in case of a leaky aquifer, theoretically, or there can be, it can have semi confining layer at the top as well as bottom, and more than that. So, even between these two semi confining layers at the top as well as bottom, one may have less hydraulic conductivity, one may have more hydraulic conductivity. So, if the top aquitard is having less hydraulic conductivity, then the leaky aquifer may be this one may be losing its groundwater volume, whereas on the other hand, if the that is the bottom semi confining layer is having less hydraulic conductivity, then in that case it could be a gaining leaky aquifer, generally even without any pumping well. So, therefore, we have even with the simplified this one, wherein the bottom confining layer is taken to be fully impervious, and there is only the top that is semi confining layer or aquitard layer for the leaky aquifer, and that too we are considering that to be having a uniform hydraulic conductivity of K dash and a uniform thickness of B dash. With this, we are in a position to determine the formation constants of the leaky aquifer, such as the transmissivity and storativity, using this the equations given. Okay, and so that so this will complete the unconfined radial flow in a leaky aquifer. And now we will go to, that is the next component of this lecture, that is the well flow near aquifer boundaries. And here let us start with the well flow near a stream, and in this case, say let us consider a stream and of course here I am exaggerating the depth of the stream, and here there is a pumping well on one side of the stream. And of course, in this case we are considering only the, so this is the stream, so this is the perennial stream. So, this is the perennial stream, and then this is the pumping well. Fully penetrating well, and we are considering so there is a bottom confining layer which is common for the well as well as the perennial stream. This is Q. Okay, let me follow the color code, that is green for this representing water, and then so this is the fully penetrating well, and here so we'll once so when there was no pumping, so this is the original water table when there is no pumping, and once the pumping starts, so there will be a cone of depression, and this is the shape of the cone of depression, fully penetrating, and this is a pumping well, pumping. So, here which is also can be denoted as a discharging well, and it is on one side of this perennial stream. Now, here so in this case the water table will have a flatter, this cone of depression will have a flatter slope away from the stream and a steeper slope towards the stream, and this one can be represented by, that is two separate this one, that is so let me redraw this one. So, here let me write here. So, this is a flatter slope of cone of depression, whereas this is a steeper slope of the cone of depression. Steeper slope will be towards the perennial stream, and the flatter slope is away from the perennial stream, and so these are the so this is the perennial stream. So, now this can be thought of as a so let me redraw so this is Q, and this is the the ground level and so this is the non pumping or the original water table, that is non pumping water table. And here, so the cone of in this case, suppose we replace this, the upstream bank, I am sorry, the near bank of the perennial stream by a barrier, excuse me. Here the resultant cone of depression so this can be thought of as a symmetrical, that is a recharge well so this is so here this is the imaginary, this is the image well, recharging image well. So which is imaginary, and then so this is symmetrical with respect to the so this recharging image well, so this is the line of symmetry. So this is the actual discharging well, which is on one side of the perennial stream, and because of the perennial stream, so it is getting more contribution, more radial contribution on the perennial stream side than the other side for this discharging well. So therefore this cone of depression shows this unsymmetrical slopes with a flatter slope on the side away from the perennial stream and a steeper slope towards the perennial stream. So, this can be explained by introducing. So, this is an image well which is symmetrical with respect to the line of symmetry. So, which line of symmetry represents the nearest bank of the perennial stream to the discharging well. And so, here these distances are say if this is if this distance is minus a, minus representing because it is to the left of the line of symmetry, and this will be plus a. So, therefore, here, so this is the resultant cone of depression, and then this is the cone of impression due to image well. So, this image well is analogous in its effect, it is analogous to the contribution by this contribution to the discharge by the perennial stream. So, therefore, the this is the cone of depression and this is the cone of impression. So, the resultant of the cone of depression in the absence of perennial stream. I am sorry, this is a so, therefore, and this perennial stream can be replaced by a symmetrical image well when which is recharging. So, therefore, the contribution of this this one, the perennial stream is replaced by a symmetrical recharging image well. So, finally, we get this resultant cone of depression as shown by this solid green line, which is the resultant of the cone of depression in the absence of perennial stream shown by this dot and dash convention, as well as the cone of impression due to the image well, which is imaginary and which is having the same, which is providing the same effect as the perennial stream. So, here, so like this, the because of the boundary. So, in this case it is the upstream, that is the near boundary of the perennial stream. So, the cone of depression will show an unsymmetrical slopes, steeper slope towards the stream and a flatter slope away from the stream. Now, let us consider the next case wherein there is a solid boundary. And So, here in this case we can also draw the, that is the, for this figure we can also draw the flow net So, here we will get, this is the pumping well, and then this is the imaginary recharge well, recharge image well, and here, so the streamlines, so they will be and then this is the boundary here. And here, so this is the pumping well, and then this is the this is the discharging real well, and this is the recharging image well. And as usual, so this is and here so like this we get so these are the streamlines for the recharging image well. And then similarly, which are radially diverging, radially outward as one, having a radially outward shape, whereas for the discharging real well, the streamlines are converging. And obviously, so these are the streamlines, and then the equipotential lines, so will be circles then similarly here the So, these are the equipotential lines. For the discharging real well. Okay, anyway, it's obvious, and so this is the equipotential line, and then so this is the here this is the equipotential line for the recharging image well. So, like this, so this is the flow net. And next we will consider the case of a barrier boundary. So far we have studied we considered the case of a stream, and now let us consider the case of a barrier boundary. And in this case, so this is the barrier boundary. And here we have a pumping well or a discharging well. So, this is Q from this discharging well, and then the static water table or the original water table. So, this is the static water table, that is original water table, and let us consider so this height as h0 from the impervious boundary, and then so this is the, and in this case the final the shape of this the water table. So, in this case it will be the reverse of the perennial stream. So, in case of perennial stream, so the cone of depression was having a steeper slope towards the well and a flatter slope away from the steeper slope towards the stream and flatter slope away from the stream. In this case it is reverse. So, because of the boundary, so the contribution groundwater contribution towards the boundary will be less. So, therefore, it will have a flatter slope, whereas the groundwater contribution away from the boundary will be more. So, therefore, it will have a steeper slope. So, in this case, so this is a flatter slope of cone of depression, and this is a steeper slope of cone of depression. So, this is just the barrier boundary. So, this is just the reverse of a case having a perennial stream. So we'll so this is so we considered in this firstly we considered the that is the well flow near a perennial stream, and next we will consider well flow. We considered well flow near a barrier boundary. So we will stop here and then we will continue in the next lecture. Thank you.